YMSC, talking about SUSY compactification and arithmetic of Calabi-Yau Varieties.
All right. Thank you very much for inviting me. I'll speak about some old work because Hussein asked me to, but also because it's interesting and there's lots of unsolved problems. So most of this is from my paper with, well, lots of this is from my paper with Candelas, De La Osa, and Dukov and Stratton. And so I'll speak about some special Hodge structures. I'll say why we care about them in physics, where some interesting arithmetic shows up, and some interesting questions which still haven't really been answered, not satisfactorily. So we're often in the case when we care about Calabi-Yaus and string theory. So families of CY threefolds. And for example, the one we saw earlier, I'll write it slightly differently, but we saw it maybe 10, 20 minutes ago. It's 5. So in P4, and psi is just some parameter. And so generically, these things are for different size, these things are diffeomorphic, but they have different complex structure. And a very common problem you run across when you study these things is you want, so find psi such that some choice of gamma, let's say, has a specific Hodge decomposition. For example, you might have, you might want gamma in H30 X. So let's say some psi star. So I'll say one example later where you come across this kind of condition. So psi controls the complex structure of your Calabi-Yau. You pick some reference integral cohomology class. So this doesn't care about your complex structure, but then you keep varying your complex structure so that say, for example, the 2-1 part and the 1-2 part of your reference cohomology class vanishes. So you want to find special points in your complex structure moduli space, something like CM points. And one place, so the example that I want to talk about comes from string theory, and it's this attractor mechanism. Okay, so what does this mean? String theory is you study this in 10 dimensions. So you consider 2B string theory. On space-time. So your space-time should be 10-dimensional, but you pick a very special space-time. You say a black hole in this, I'll say what a black hole is in a second, times your Calabi-Yau threefold. So this has 6 real dimensions, and this is 4 real dimensions. By black hole, I just mean it's R13, but it's like R13, but with a special metric. So the metric here is, I say it's a black hole because this has a very special metric. It looks like 2 e to the r dt squared plus d5 squared. Okay, so and on here, you should your metric is your Calabi-Yau metric. So you consider 2b string theory on this space. U is going to be some function that you have to fix. And I needed one more definition. So definition. So there's a central charge. Is some function, say z gamma, which depends on your parameter, psi here, is e to the k over 2. And e to the k over 2, e to the, say, minus k, is also given in terms of I. So omega here is the holomorphic 3 form that was mentioned in the last talk. It's this alpha. And so you compute some, and this you can use the Riemann bilinear identities to re-express just in terms of the periods of your holomorphic 3 form. And the periods of this. The periods of this is an integral cohomology class, so its periods are going to be integers. And actually, you can, it's also very special. I mean, this isn't so important, but right now. So P, let's say, and so get out the way. So is a number, yeah. It's a function. It depends on your choice of gamma. Your gamma is really, after you pick a basis in your cohomology, it just depends on a bunch of integers, 4 integers. These integers have an interpretation. They're the electric and magnetic charges of some black hole, but you can ignore them. They're just four integers. And it also depends on the complex structure parameter. So this is the parameter of your Calabi-Yau.
I'm just confused because this form omega psi, from what I remember, it's only defined for constant.
Yes, that's a very, very good point. So this is a physical, well, absolute value of this is a physically meaningful quantity. It's like the mass of your black hole or something. So yeah, you're right. This is only defined up to a overall constant. But look what happens. If I rescale this by a constant, this e to the k over 2 also picks up also gets rescaled because it's defined via the same holomorphic 3 form. So this z only changes by a phase. So its absolute value is well defined. That's a very good point. Yeah, so it's a function. It depends on your parameter and your choice of charge vector, some integral cohomology class. And so this black hole should have some special property called supersymmetry, and this just gives you some flow equations on this kind of the psi plane on your complex structure moduli space.
What is X though?
Sir?
The X.
X is a oh, x psi. You integrate over your Calabi-Yau. And same here. This also depends on psi. So I'm saying your space-time should be 10-dimensional. It's some some space with this particular Riemannian metric, these t is time, and these are the normal polar coordinates. And you also have your Calabi-Yau threefold. And the supersymmetry of the black hole gives you some flow equations. du by d. So this u is a factor which appears here. R, rho, 1 over r, is z. I'm going to use gamma, psi, and d psi. D rho is minus 2 e to the u rho g psi bar. This g is okay, so you want this black hole to have some special properties and called supersymmetry. And what this tells you is that this function u and psi should also depend on radial distance from the horizon of this black hole. That's this r here. So you can if you forget all this for now and just care about the fact that we have some flow equations on our complex structure moduli space, and they have some very special properties. I'm just trying to motivate why we would ever end up in this kind of situation where we care about the Hodge decomposition of some reference 3 form. So the claim is, so 1, the flow on psi plane has a sink. What does this mean? Well, you pick some gamma. There'll be and so this will define a flow on your psi plane. Your psi plane is your complex structure moduli space, and these flow lines will end up at some fixed point. And that's why it's called the attractive mechanism, because of this attractive flow. And the claim 2. So the endpoint.
The second differential equation is independent of the first one. That's why you consider just differential equation of psi.
Yes. If you want, you can redefine rho and absorb all the. You can instead of rho, you can use some.
So rho is a real parameter.
Rho is a real parameter. It's the inverse of this radial distance. And if you want, you can redefine. You can rewrite this as a single equation for psi, where it doesn't depend on u. But
then this flow that you put it there, it's just from the second differential equation.
yes,
And this plane is the psi plane. The
Yes.
imaginary part of the
exactly.
The second one depends on u, and u comes from the first one. So
You can, I haven't written it down, but you can change your parameter here, and you can absorb the u dependence into your choice of parameter and get just a flow for psi. So u will only change how quickly you move along the flow. It won't change the flow lines. And so it has a sink, which only depends on gamma. And 2, this is an exercise, which I will skip, but it's not so difficult. You just need some identity. At psi star, gamma is in H003. So this is Z.
What is K there?
K? Oh, K is this K. So your complex structure moduli space, or some cover of it, has a metric. It has a Kähler metric, and this Kähler metric is this Kähler potential, which is this K. And you take derivatives of this Kähler potential, and it gives you this metric, components of this metric here. And so, okay, we end up in this. The fixed points are very special because your charge vector, your choice of cohomology class, has a very specific Hodge decomposition at this fixed point, and it's of 3,0 plus 0,3. How do you prove this? Use some properties of the periods, which I will skip in the interest of time. Basically, you want this side to vanish at the endpoint. You can ignore this if you like. This will only vanish, and okay, if you assume it's regular, so this won't vanish. So the only things that can vanish is this. This depends on the periods. The derivatives of the periods have some special Hodge decomposition, and you use these properties to argue for this. It's not such an interesting derivation, is it? But it's like, it's 2 lines, it's not. But yeah, it's 2 lines after you know some identities. And definition. So sometimes you can end up in a situation where you have 2 different gammas which lead to the same attractor point. These are these attractor points of rank 2. So an attractor point of rank 2 is, so psi, let's say star, is an attractor point of rank 2 if there exists some gamma 1, gamma 2, in H3 xz, where they're both say psi star and you also require that they're not proportional. Okay, so these are the more interesting attractor points. If you pick a random gamma, you will always just you can always just solve these, find some attractor point. These things are, there are some conjectures which say these attractor points are dense, but the much more rare ones are the ones where you have 2 different gammas leading to the same attractor point. These are these attractor points of rank 2, and there's some generalizations of CM points for Calabi-Yau threefolds. They're like CM points. You have some splitting of Hodge structure. And how can you find some examples? Well, the simplest way this can happen, so this can happen at fixed points of symmetries. And for example, I won't use the quintic, the mirror quintic, because we don't think this has attractor points of rank 2. But So you can consider some Picard-Fuchs equation. I'm going to call it AESZ101. This strange name is from a list by Almqvist, Enkelfart, Van Straten, and Zudillen. You can find, so there's a list of potential Picard-Fuchs equations for families of Calabi-Yau threefolds, and this is the 101st entry in this list. So what's this Picard-Fuchs equation? It's, well, the operator is given by, I'm not going to write the whole thing because it's kind of long. 24, theta to the 4. Plus, okay, where theta is phi, d by d phi. I use phi instead of psi for whatever reason. L annihilates the periods. So I pick B, so I pick some choice of A cycles and B cycles, which generate the integral H3 of your Calabi-Yau. I integrate the holomorphic 3 form, which was called alpha in the last lecture. I integrate this over these homology classes. I get the periods. They're annihilated by a Picard-Fuchs equation. And it's this Picard-Fuchs equation. So I'm interested in special points, so special values of phi, where the periods have some special property, which tell me that you have this lattice generated by some gamma 1 and gamma 2, some integral cohomology classes. So this, well, there's some underlying Calabi-Yau in this case. This Calabi-Yau is singular. Let's say some x phi is singular at, okay, I guess I can skip this. I'll just tell you the result. There are some singular values of phi, and so can check. You just play around with this differential equation, find some solutions, and you find that the periods have a symmetry. Let's call this guy A. And so you can interpret this symmetry of the periods geometrically. So A represents a map from H3 x at, say, at phi, into coefficients, to H3 of x 1 over phi. Phi is like psi. It's a parameter. It's a complex structure parameter. I use phi. This is some notation that pi. This pi is, sorry, I should have said. This is pi. Okay. So the periods have a symmetry, and this matrix, the integer matrix A, you should interpret as a map from the cohomology at phi to the map at to the cohomology at 1 over phi. And now you look at the fixed points. At the fixed point, you have +1 and -1. So this A is some involution at the fixed points. A is an involution which splits the cohomology at the fixed points. So A has eigenvalues. +1, +1, -1, -1. Phi equals +1 is, let's say, x at phi is 1 is smooth. You can check this. -1 is singular, so we don't care about this one. But this guy is smooth. And it turns out this A will split the cohomology at phi equals 1 into two eigenspaces. And the plus eigenspace will have Hodge numbers 3, 0, plus 0, 3. And so this phi equals 1 is one of these special attractor points. And -1 is different.
There must be some morphism from x phi is 1 over phi, right?
Yes, exactly. Yeah. But yeah. You can write it down explicitly. Yeah, you're right. There is. But to see the splitting of Hodge structure, you just use the periods. This is smooth, and the periods tell you about the splitting of Hodge structure. Okay, where you can check. So okay, this is a numerical result. Pi at 1 is equal to e to 1, 6, 1, 3, 2. 0, 5, 1, 0. And so e to 1. And e to 2 is -1, minus I. And this, the fact that the periods, well, conjecturally, satisfy an identity like this, tells you that you're at an attractor point of rank 2. These guys are, they're the +1. Let's call this gamma 1. Call this gamma 2. So gamma 1 and gamma 2 are +1 eigenvectors of A. And you can see that, maybe I shouldn't have called them gamma. They are the periods of elements in H3 XZ with Hodge numbers why is that? Well, to get this, you take the real part of pi, take the real part, you have to complex conjugate. This is the periods of something with Hodge numbers 3, 0. So you get the complex you get 0 through where you complex conjugate, and the same. So this must be the periods of a cohomology class with these Hodge numbers, and the same thing here. So this is an example of one of these attractor points of rank 2. What?
Phi equal to 1.
At phi equal to 1, yeah. So phi equals -1 is also a fixed point, but it turns out that phi equals -1 is singular. You can say more. So there's a theorem, which I'll just quote. As a cohomology class, you can take where so it's the same K that appeared earlier. It's this scalar potential. Now it can also act as a connection. If you take this covariant derivative of your holomorphic 3 form, it will have very specific Hodge numbers. So Griffith's transversality tells you if you take derivatives, you get something with Hodge numbers 3, 0 plus 2, 1, and this term can kill the 3, 0 part. So by taking a very special derivative of the periods, you can get the periods of some 2-1 form, say the harmonic 2-1 form, because. And you can also compute this. So again, numerically. So d phi pi at 1. Now let's say e to 3. 10, 1, 5, 2 plus 0, 3, 1, 0, and just some numbers. They're interesting numbers. They're going to be some L values, and well, I'll talk about that later. And again, these guys are -1 eigenvectors. And they generate maybe this is a better way of writing it. H3x1 z intersection And so this is an example for one of these attractive points of rank 2. They're like CM points. I mean, you have here H21 is equal to 1 for this Calabi-Yau. So H3 has Hodge numbers 1, 1, 1, 1, so this kind of splitting tells you there's a two-dimensional, there's a splitting over Q into something like this. And this is kind of like CM. When you have CM for an elliptic curve, you have Hodge numbers 1, 1 in middle cohomology. You have splitting over some Q root minus D into 1, 0 plus 0, 1. And here's an example. So far, there's no arithmetic. But you're kind of forced to use you end up using arithmetic when you ask for more examples.
D is going to be explicit, no?
D?
It's capital D, Q square root of minus D.
Yeah, it depends on your CM field. So if you have an elliptic curve with CM, it has its Hodge numbers, and you have to use coefficients in this field in order to. Yeah, exactly. So D is going to be some explicit number. So question. can we find rank 2 attractors which don't arise as the fixed point of some symmetry phi goes to 1 over, let's say, something phi prime. And so if you have the Picard-Fuchs equation, especially when you have one parameter examples, the symmetries are typically kind of easy to see. You just look at all the singularities, you look at the solutions around the singularity in some whatever basis you want, and you try to move the singularities around to identify symmetries like this phi goes to 1 over phi. And if you're lucky, the fixed point will have some splitting of Hodge structure. But there are examples which don't arise like this. There's no obvious symmetry. And how do we find them? And for this, we need to use some techniques from arithmetic geometry. So the main technique you use is, well, you do a computer search, and the main computational tool is this zeta function. So what's it called? Local zeta functions. And how are they defined? They have a, so for example, so consider x psi. Again, it's the, e.g. the mirror quintic. Where now your parameter psi is in Q. It can be in some number field, that's fine. So you just count number of points. So you have some defining equation, you reduce a mod p, you count the number of points in this over some finite field, and define Zp of t sum over, let's say r is 1 to infinity. Oh, no. Exponential of the sum, r is 1 to infinity. Let's say over r t to the r. This is this local zeta function for some prime p. And, okay, this is, to the experts, this is very, very well-known stuff, but there are theorems, the Weil conjectures, which tell you, the first one tells you that this is rational. So the Weil conjecture 1 theorem 1 says Zp of t is p1 p2 minus 1 t p2n t. And so n here, let's say the complex dimension of x at smooth points for smooth psi. And there are some, the degree pi of t and the degree, pi, is given by the Betti number. And so I'm not an expert on this stuff, but
It's all assuming that the variety is smooth.
yes. And the way this stuff was proven was by realizing these polynomials as characteristic polynomials. For P and this is some suitably defined cohomology theory, some crystalline cohomology, I think, which makes sense mod P. And these things can be computed. H, let's say, B3 of xi is 4, implies the other vague conjectures fix lots of this. The form of this ZP, there's some functional equation which swaps some of these polynomials around. So this is H11. And so the only interesting part of all this is this polynomial here, which corresponds to the action of some Frobenius on H3. And the claim is at a rank to attractor, you can diagonalize you have Frobenius, or with the star probably. Which implies into two two-dimensional blocks. And this implies that ZP should factor. No. And this is actually has been proven by Yui. And I'm going to get this name wrong. I think it's something like this. I forgot to write it down. Govo. Gover.
You assume that the attractive point is defined over rational numbers.
Yes.
But it might be
That's true.
right number fields, etc.
When that's true. And actually, so we have examples where it's defined over a number field, and there I don't think it's proven. The paper was called rigid. I forgot to write it down. It's rigid Calabi-Yau threefolds over Q are modular, or something like this. I forget the exact name. And in the end of this paper, they prove that whenever you have this kind of splitting of Hodge structure, they prove more. Whenever you have the splitting of Hodge structure, this will split into two quadratic factors, and each factor is associated with a modular form, one of weight 2 and the other one of weight 4. So in this case, that P of t is going to look like 1 minus alpha p pt plus p cubed t squared 1 minus beta p t plus over dot dot dot, the less interesting part, and there exists f2 for some modular form for some gamma of n such that f of tau is sum over alpha n qn, and these alphas are the same alphas that appear here. These things are Hecke eigenforms, so it's enough just to know the prime coefficients. And there's another one of weight 4. Okay, so the strategy for finding these things is just to look for these factorizations. There's some work by my collaborators, Candelas, De La Osa, and Van Straten, that give you algorithms that let you very quickly compute these local Euler factors, these zeta functions. So
in this modular forms, they cannot be, right? For each p, you have a different.
No. You have one modular form, and at every p, you pick out a different Fourier coefficient.
Oh, okay.
So it's one. Yeah, there's the
The alphas are the coefficients.
exactly, yeah, and these. So they're Hecke eigenforms, which means that if you know just the prime coefficients, then you can fix the other ones.
Yeah.
So, and of course, there's some bad primes where it's a bit more complicated. So So strategy for finding rank 2 attractors is compute ZP of T for many P and all phi in FP. Then, so this is a computer search. So then you look for a polynomial. G of phi in Z of phi such that the numerator of ZP of T factors like in, say, star. Let's call this star. So at the roots of G of phi in FP. So you just, this is integer coefficients. You run over the coefficients and the degree. You do a long computer search, and eventually you'll end up with some candidate. And then, once you have this candidate, then now you solve G phi is 0. Now you solve it over C, and you check with periods that the Hodge structure splits. And so there's an example. So after you do this computer search, you end up with, you find some phi, such that whenever you reduce it mod p, this numerator factors. Once you have such a thing, you use the periods, and you check that you really have an attractor point of rank 2. And okay, so this is a numerical result. You check that pi at -1 over, so for, again, this is another one of these Picard-Fuchs operators from this list. We know it does correspond to some Calabi-Yau, which we know. You compute its periods, and you find, now you can say more. Because we have these modular forms, which you know from the local Euler factors, once you have this guy, you can check with the periods that the periods look like this. 8 at phi is -1 over 7. 0 phi plus, minus 14, 2 pi I, at 2. So it's an attractor point of rank 2. You see these the periods of some integral cohomology classes. You see them numerically, but you also see some very interesting coefficients. And these coefficients come from, you take the weight 4 modular form. What did we say? We said beta and Qn. And there's some Mellin transform, which gives you an L function from this guy. and you evaluate at some special points, and they appear as coefficients. We check this numerically.
Is it the same F4?
It's the same F4. It's the one that you get from the local Euler factors. You compute.
Is it a coincidence?
No. No, I think it always seems to work like this. Sometimes you have to be careful. Instead of just computing the period, instead of computing the critical values of the L function, it's a bit more complicated. You compute periods of this guy, which, you know, you have some Pugasato variety which has holomorphic 3 form, F4, d tau, wedge dz1, wedge dz2. It could be that you have to, it's not just the L functions that appear as coefficients. It could be that it's some other period which appears as coefficients. But I think this, yeah. If you have some correspondence with the Pugasato variety, then these coefficients should appear as in the periods of the holomorphic 3 form. And so that's the interesting result. And the bit that's, and okay, so you can check many more examples like this. The open problem, and which we can discuss at Aquamatica, I think is the most interesting part of all this, is you try to understand, well, in the beginning, we started talking about some black holes, there was some attractor mechanism going on, and you find these attractor points of rank 2, you find them using some techniques from arithmetic geometry, and it seems these modular forms come along. I mean, there are theorems which tell you, okay, well, at least when, so in this case, phi is rational, so if you could prove the splitting of Hodge structure, this would be a theorem. There are theorems which tell you that these modular forms come along. And so from the black hole point of view, from the string theory point of view, there's really no clear explanation for what these modular forms are doing. But there is a clue. So the clue is that it's known that these periods, when you evaluate them at the attractor point, you can take ratios and compute the horizon area of the associated black hole. So you pick some, let's call this one gamma 1. Let's say these don't generate, these generate as some sublattice of your 3, 0 plus 0, 3 lattice. The actual generators of the lattice are slightly different. Plus L, 0, 0, 2, 1. So, okay, you choose, these are the periods of some cohomology class. All right. So if you pick some K and L integers, and you check, I'll just give you the result. So the horizon area of black hole with charges, with charge gamma is A, which depends on this, say, KL. You divide by 4, this is convention, and there's some simple formula involving the periods, actually involving the central charge, which involves the periods, which looks like this. And, okay, why am I telling you about the horizon areas? Sorry? Sorry?
Is this an actual equality?
It's an inequality. So there's some simple formula involving the central charge. There's basically the absolute value of the central charge is basically this area. And the central charge, that which I rubbed off now, comes from the periods. If you, at the attractor point, the periods we have this conjectural formula for, so you just massage this into this form. You take some special ratios. I haven't written down the formula. It's basic. I might forget some factors, but it's basically, and then you evaluate it at the attractor point. Maybe some rational factors, I forget. So, but, okay. Why am I writing down the area? Because I think this is a big hint for what all this modularity means in terms of like something a string theorist might care about. Because it's believed that the horizon area of a black hole is a measure of entropy. And there are two ways of measuring entropy. There's there's a thermodynamics, but then you also, if you remember thermodynamics class, this is like a thermodynamic entropy, but you should also be able to recover the same answer by doing some microstate counting. So let's say there's some KL. This is an integer, which is, these are microstates, something, whatever they are. If you have some quantum theory of gravity, you should be able to count microstates of black holes. And this, for large K and L, should grow like this. And there's a story by Strominger and Waffa, which tries to identify what these microstates are. You can get them by counting some special minimal submanifolds or some sheaves on your Calabi-Yau. So there's some kind of well-defined counting problem which recovers these microstates. There's something like Donaldson-Thomas invariance. And what this formula is telling you is that their asymptotics are controlled by these ratios of L values. So if you want to understand what this modularity means in terms of something that string theorists might care about, this is probably the place to look. You want to find some minimal submanifolds inside your Calabi-Yau, compute some Donaldson-Thomas invariance. Yeah, and if you believe what Bekenstein-Hocking and Strominger-Waffa are saying, then their asymptotics should be controlled by these ratios of L values. And that seems like a quite deep statement, and it should be, we can discuss more in Aquamatica about how you might attack this problem.